In section 9.7, we're going to be looking at modeling the spread of a disease with differential equations using the same techniques that we've looked at in 9.6. So this is very useful for today, as what we're dealing with in this pandemic is the spread of a disease. And although the differential equations we're going to be talking about are very simplistic in the model, this same model can be used to model COVID-19, and it just gets more complicated as you add more factors into what's going on. But these base differential equations we're going to be talking about are the base that we study a lot of infectious diseases. We're going to try to reference COVID-19 in this video so we can kind of understand what's going on. So there's a few variables we're going to talk about. Note this is called the SIR model based on these three letters S, I, and R, which we're going to describe right now. So S is the number of susceptible people in a population. It is the number of people that are able to get infected by the disease. I is the number of infected people with the disease in the population. And then there is R, which is the number of recovered people, or people who are susceptible, who are not susceptible, such as people vaccinated. So it's important to note that the total population that we are talking about here is going to be equal to the number of people who could get the disease, plus the number of people who have the disease, plus the number of people who cannot get the disease, as that's what R is, the number of people who can't have the disease. This is the number of people who could get the disease plus the number of people who have the disease plus the number of people who cannot get the disease. And it's important to note when we're talking about R, the number of people who cannot get the disease, oftentimes that's people who have previously had the disease as they get antibodies in their system and they're no longer susceptible to it. The best example of that is chickenpox. Everybody can get chickenpox only once, so once you have it, you are now recovered. Or vaccinated people are recovered. And note that this is one of the details we can talk about COVID-19, where this model isn't perfect because there are people who have been vaccinated who are still susceptible to the disease, as there's a 95, 97% efficacy rate in the two big vaccines, Pfizer and Moderna. So all these little details can make differential equations more complicated, but again, this base model is what we're kind of going off of. All right, so let's look at the differential equations. We're going to look at the susceptible people, the infected people, and the recovered people separately. And note that we're only going to be dealing with two differential equations instead of three, and we'll talk about why in a second. So as the disease progresses, more and more people are infected with the disease. It's spreading. And that means that the number of susceptible people decreases because some of those susceptible people become infected. So this is as susceptible people get infected. There's no way that the number of susceptible people can increase because it's already the biggest number at the start. So it's just going to decrease, and it's going to do so at a rate proportional to both S and I. If you have a large number of susceptible people, it can decrease further. And if you have a lot of infected people, that's also going to influence how fast this is going to decrease. So this is like the idea of the encounters idea in the previous video, where now you have susceptible people and infected people are, you can think about predator and prey. The infected people infect the susceptible people and turn them into infected. Right, so this is like the idea of the encounters in 9.6. We're going to have A just be a constant of proportionality. We're going to talk about what that value actually means at the end of this lecture. All right, so the number of susceptible people is decreasing at a rate proportional to both S and I. As the disease progresses, the number of infected people is going to grow at a rate proportional to the number of susceptible people. So we're going to grow at a rate proportional to the number of susceptible people being infected. That's this ASI. That's the number of encounters that we're having. As the number of encounters increases, then so will the number of infected people. It's going to do so at a rate proportional to this idea. This is the big idea of the disease growing exponentially. Right, and this is why when we first think about COVID-19 in America, we have just a few cases at the beginning, and that's because the number of infected people is so small, even though susceptible people is very large. But then as the number of infected people grows, then the disease starts growing exponentially. Now there's not just 2 cases, there's 20 cases, now there's 200 cases, now there's 200,000 cases, and now we're talking about millions of cases. So it's growing exponentially, and that's the term that we're kind of looking at that. There's another factor when we think about infected people, and that is that these number of infected people get removed from the population. And that's in one of 2 ways. Death is one way that an infected person gets removed from the population. And unfortunately, that's something that we are talking about in this lecture a lot. Or somebody can recover. And especially in the case of COVID-19, it's recovery that actually is the big way that people get removed from the infected population. And note that there is some details we could have because now we know that somebody can get COVID-19 twice, right? So it's not necessarily once you recover, you're no longer susceptible or infected, you're recovered. But in a simplistic way, we can kind of think about that. So as the disease goes on, more people get infected, which means that more people recover at the same time. So there is a negative effect of infected at the same time. All right, we have a constant B that we're going to look at to see how fast somebody recovers. That's what that's tracking. Again, we'll say that in a later page. All right, so then we're going to assume that once an infected person has recovered, there's antibodies in their system and they're no longer susceptible. That makes these differential equations easier. We don't have to add extra terms. We don't have to deal with a lot more variation in what we're talking about. So therefore, the number of recovered people is just going to be that same BI that we're talking about. As the number of infected people increases, that means the more recovered people increases. So dr dt is going to be BI. It's the exact same thing that we had before. So note that because the total population is equal to S plus I plus R, if we know information about, so if we know what S and I are, then we also know R. If you ever know what both values of S and I are both are, then we don't have to think about that last value, the number of recovered people. We can just figure that out with a simple subtraction of total population. So because of that, we don't need to use the last differential equation. Is that information is encoded elsewhere in the other 2 differential equations. So you're not going to see that dr dt written pretty much anywhere in this section. All right, so now let's talk about what we can do with those differential equations. The first is that we can look at these constants of proportionality, A and B, as they give us important information about the disease. So the first one is the value of A, and that tells us how infectious the disease is, how quickly it's going to transmit to susceptible people. We can find A by solving for the differential equation. We have ds dt equals negative ASI. If you divide by SI by a negative SI, we have this formula we can find for A if we have certain values. But again, what's this is telling us is that is how infectious it's going to be. So if you have two diseases, they could spread very differently depending on how infectious they are. And in fact, we can think about just COVID-19 and its variants that we have as well. There are different variants of COVID-19, and they infect people at different rates, some more infectious than the others. And tracking those things is very important, and it's going to do so at different rates. Moreover, different diseases itself have different infectious rates. A good example to think about infectious rates is measles versus Ebola. Right, these are two diseases that you may have heard about. Measles is one of the most infectious diseases that we've ever seen. It is extremely infectious, but at the same time, it's not as severe. This is kind of like the same as COVID-19. You might be thinking COVID-19 is not so severe for many people, but it's very infectious. That's kind of like what measles is. Whereas Ebola is very severe, but it's not as infectious. So it's kind of a different sort of thing. So it's harder to transmit Ebola, but if it does, it's a really big deal. Measles, on the other hand, transmits very, very quickly, right? And we can encode that information with the value of A. If A is bigger, that's going to be more infectious, and how we're talking about that. In that same vein, the value of B tells us how quickly an infected person is going to be removed, either by death or recovery, right? Are you sick for a long period of time, or is it a very quick kind of thing and then you're removed? And that time is important when we're talking about this change, right? How long are you infected? A lot of times in diseases, we talk about how before you're symptomatic, you may be infectious for a certain amount of time, or after you're symptomatic, you may be infectious for a certain amount of time. And those details are encoded in this value of B, which tells us how long it's going to be till we're removed. In a similar vein, we can figure out B by solving for the differential equation di dt. If we know the value of A, we can find the value of B. So lastly, we can think about this idea of a threshold value. So these two constants, A and B, can give us this other constant called a threshold value, B over A. And this is an important value in tracking diseases. So if the number of initial susceptible people is above the threshold value, then we're going to say that this disease will spread if there's no other influence going on and will become an epidemic. Right? It's going to expand into the total population eventually. If the number of initial susceptible people is below that threshold value, then the disease is going to just die out, it's not going to spread, and it's not going to become an epidemic. Right? And this is kind of tracking, again, how quickly you can recover versus how infectious it is. And then it matters how many people that we are talking about. So we're going to do a couple exercises in this section thinking about threshold value. And again, it's just looking at these two values, A and B. And we can say that if the number of susceptible people is bigger than that value, we're going to have an epidemic. It's going to have enough infection that's going to spread to everything. And it's not going to become an epidemic otherwise. All right, in the next video, we're going to look at a big practice problem. We'll go through a few details. Again, this is not a very long section in terms of the problems that we can do. We have these differential equations. We can answer some questions about it, but really we're just looking at kind of a big application and some things that we can do with differential equations.